Hello everyone, welcome to Dr. Ravi's Academy. In today's class, you will be learning the derivation for ratio belt tensions for a flat belt drive. Now let us look at this flat belt drive. I am considering larger pulley above and a smaller pulley below, and I am connecting these two by means of a flat belt drive. Assume that this is the smaller one is the driver and the larger one is driven or follower. Driven pulley, driver pulley. It's rotating in clockwise direction. Obviously, what happens? Let us see here. This becomes a pulling side of the belt. So this becomes a tight side. I am denoting it by T1. T1 is a tight side tension. It is a tight side tension. And the other side, this is slack side. I am denoting it by T2 and it is slack side tension. Now, I would like to derive the expression for relation between T1 and T2 when it is passing over a driven pulley of some size. Let us select an element. This is my element. And let us analyze this angle. I am treating it is d theta. At an angle theta from the beginning of contact. This is a total angle of contact. It is, let us treat that it is beta. Angle of lap is beta. It is angle of lap or contact is beta. Now, I have selected element at an angular displacement of theta, and that I would like to magnify this view. Let us consider this element symmetric about the vertical line. Obviously, this is at an angle d theta by 2 and this is also d theta by 2. Observe carefully here from geometry, when this is d theta by 2, if you draw a tangent here, this angle is also d theta by 2 and here also it is d theta by 2 from geometry. Both are symmetric, right? And observe carefully here, I am denoting it, the tension in the belt is T1, left side, which is connected to the slack side of the belt. And gradually there is an elemental increase in the tension. I am denoting it by T plus elemental increase, that is dt. And both are, it is, inclined at an angle d theta by 2. And let us draw the complete the free body diagram. You have normal force, let me call it as dn on the belt, and frictional force which is opposite to the direction of the motion, df. This completes the free body diagram of the element of the belt. Now I would like to apply equations of equilibrium. So let me write here sigma fx is equals to 0. Sum of all the forces along the, this is my x direction, this is my y direction, sigma fx. So it becomes t plus dt into, it is cos d theta by 2, and which is positive. Here the other side minus t into, it is cos d theta by 2, which is negative, the other side of the x-axis. And apart from that, you have minus the frictional force df is equals to 0. These are the three forces. 1, 2, 3 forces along the x direction. There is no component of this normal force because which is along the y direction. Now for small angle d theta, you can just ignore what is cos d theta by 2 becomes, it is approximately 1. So then you have t plus dt minus t minus df is equals to 0. T gets cancelled and you have df is equals to dt. This is equation 1. Let us write down what is sigma fy is equals to 0. Sum of the forces along the y direction. It is dn is equals to you have these two are in opposite direction, that is t sine d theta by 2 and plus t plus dt into sine d theta by 2. For small angle d theta, here this becomes sine d theta by 2 becomes, it is approximately d theta by 2 for small angle. Now the equation becomes, it is dn is equals to, it is t into d theta by 2 plus t plus dt into d theta by 2. By neglecting elemental quantities, this equation can be rewritten as t into d theta by 2 plus t into d theta by 2, and this dt into d theta by 2 can be ignored. This becomes t into d theta. My equation 2. Let us observe carefully. Equation 1 is equation for the frictional force, and equation 2 is dn is equals to t d theta. This is for normal force. You know very well the relation between these two. The frictional force df is equals to mu times normal force. And substitute both the values from equation 1 and 2. You have here dt. It is dt is equals to mu times t into d theta. Let us rewrite and integrate. You have dt by t is equals to mu times d theta. By integrating, let us observe carefully the tension. From left side it is a T2 right side it is T1. Here it is T2 to T1. The angle theta value is 0 to beta. It is 0 to beta. These are the two limits of integration. And you have, as you know, that integral of 1 by t is ln of t, natural log of t, is equals to mu times beta. Mu times beta. Right? Now, you can substitute the limits. It is T2, it is a T2 and it is a T1, T2. This becomes ln of T1 minus T2, that you can rewrite it as minus becomes divided by ln of T1 by T2 is equals to mu beta. And lastly, if you remove this natural log, you have T1 by T2 is equals to e to the power mu beta. This what is the required expression or the relation between the tensions of the flat belt trap. T1 by T2 is equals to e to the power mu beta. I hope you understood this particular derivation. Let us practice it.